Okay, good, that's what we're saying. Yeah, what do you guys think of that? Good one? Yeah. Yeah, once more briefly, you just take the original exam question, you know, solve all the way for x of t, but then you can go back, you have enough information here to get y of t as well. A bunch of undetermined constants, but with these four initial conditions, this one being crucial, of course, with that initial speed that I've indicated, you're gonna get circular motion, you're gonna locate that origin. And so the radius of that circular motion is gonna depend on V naught, Q, and B. And M, right? Good, so yeah, we'll leave it right there. Let's see what else was on here. So then we have the inverted cycloid. So here you have to remember your chain rule. Okay. So what did we have here? We had R equals R theta minus sine theta cos, no, 1 minus cos theta, is that right? Cos theta minus 1. Yes, cos theta minus 1. Good. Theta equals theta of t. So we wanted to do V equals dr over dt. And you have to remember that you're doing a chain rule here because r of t, dr d theta d theta dt. Okay, so you're gonna always pull out a theta dot here. You're gonna get V, you're gonna get V squared equals this vector dotted into itself, which is an important one. And then I said, oh, and then you're going to get the acceleration equals dv dt, which is a more complicated expression. So we'll do a little more with this one. So these were to be calculated. Then we had, since it's the inverted cycloid, and we were looking at it under gravity, we wanted to know how fast it's going down here at the bottom. It's 2R. If you released it from rest right here, release it from rest right there, you just use simple energy conservation. So you're going to end up with 1/2 mv squared at the bottom will just be all the potential energy you have there, so it'll be mg times 2r. And so you can get the speed that way. But what you can then do is solve for how fast. So that was one thing to do, and then theta dot at theta equals pi, because remember this is a parametrization, so then you can actually get theta dot, an interesting result. And theta dot at theta equals pi means how fast that parameter is changing down there when you're at theta equals pi. So I wanted to add one more thing to this. Just occurs to me here. Yeah. So I wanted to add one more thing to this, and that is the acceleration. Okay? So the acceleration, this is, remember, this is a Cartesian vector here. When you differentiate it all out, just dv dt. What we want to do is find, so I'll write here also, find a sub y at the bottom here. So find a sub y theta is equal to pi. And we'll get into general expression for a sub y with n equals pi just by evaluating this thing. But then, and when mass is released from rest, at the origin. This will be an interesting one because, so you're going to get the acceleration here, right, when it's been released from rest, or in general. But yeah, you want it when it's released from rest because there will be no there will just be an a sub y. But anyway, remember a equals b squared over r. Okay, never forget that one. So that solution here, since we have v and a, should give us the radius of curvature of the curve down there, which none of us knows off the top of our head. Right? The radius of curvature is obviously wider than just 1 over r, than 1 over this r. So that'll be interesting as well. Okay. So origin, and then finally what is the radius of curvature? Radius of curvature. I'll just say at star, and we'll name this point star. There we do. So let's turn that into a good problem as well. These are all really rich, a lot going on here. Good. Let's see what else we had. Yeah, then we had that central force problem that shouldn't have really, we had actually done this central force problem, just with different letters. So I'll go ahead and erase this. So I don't think there's anything special to do on this one, but just remember, I gave you, so 3 was central force. Now remember, we have m mass times acceleration. This is the form of central force where this is with respect to an origin, where this is a unit vector here. So what we had was f of r was minus b, so just some constant. So you should have just integrated up b times r and just take it from there. Now a couple people, when it got to that, and just find the effective potential, etc. Okay. So there you're just following through with the regular central force program. A couple times people misinterpreted this absolute angle formula. Namely, when you have this, r times u double prime over u prime, evaluated in r, it's a mistake to put the effective potential in here. Sometimes people do that, right? You gotta remember, now you're just using the original potential. The effective potential is that L squared over 2mr squared plus the u of r. Okay. And this is the one, which is also just this one, that goes into this formula. In this case, the answer is pretty simple. What is the second derivative of this function right here? It's 0. Yeah. So you're just going to end up with pi over root 3. Interesting result. You can actually build a device that does this as well. We'll study it next semester. We'll also talk about it now. If you have it's called a central force table. If you have, say, a smooth table, a frictionless puck, you can do that with some kind of hovering air puck, and you have it connected to a mass that hangs under the table like that. Then the potential for this system is of this form, unfortunately, you can't use this formula for that. So you're actually not gonna get this exact result. You cannot use this formula because you have two masses here, and you only have one mass there. But it's an interesting problem with this type of potential, and we'll get there next semester. We'll talk about it some more.
Somehow like use reduced mass.
You'd have to be careful, yeah. The thing is, you get the reduced mass here, you do get that, or you could, but you don't get it here. Because this one, this mass, for this table problem is only the one up on top. Whereas, this mass would be the whole thing. Anyway, it's good. And then we had the absolute angle for this other u of r. So I'm not going to add anything to this problem, and I don't think I'll add anything to problem number 4 either. Although I'll say something beyond what we know here about it. So on this one we said, let's look at the potential energy minus alpha over r, and this time we're taking a small half kr squared. So where would this come from in an astronomical context? This could actually be the potential if you had a uniform, very, very dilute dust that your solar system is moving through. And then you'd actually get this form of potential by Gauss's law. It's something you've seen before in E&M probably when you talk about the uniformly charged sphere. So you would get this, but of course this would have to be very small, otherwise you'd be choking on dust. But, so this is an actually interesting problem here from the standpoint of, are we moving through something that's that, dilute, and it would affect the absolute angles. Okay. So you can calculate the absolute angle, and you can also see what your small quantity is going to be. Unlike the beta over r cubed that we talked about before, this one actually is for all r, okay, because it's being assumed that it's just uniformly distributed. But yeah, what if we factor this out? What do we get? K r cubed over alpha, right? So the point being that this is going to be our small quantity that's much, much less than 1 when we go ahead and evaluate that thing. So you're going to do the same thing we did on our homework assignment. You're going to have this pi root 1 over 3 plus r u double prime over u prime. And you have to do a little bit of arithmetic here, but when you do it, you're going to get it into the form of pi times, and I'll just write the general form just to remind you guys. Yeah, I get a pi root 1 plus z, where z is a small quantity, 1 plus 4 times z. What is my z? Yeah, I'll just write this down. Kr cubed over alpha, right? And then if you've got this and you're saying z is much less than 1, then you do your Taylor expansion first order, you get a really nice result that you can, like I said, you can give to the astronomers to get back to you on. Okay, make sense? Yeah, we did that in the one here. So I don't think we'll add anything to this one. I just wanted to give that context. Do you guys remember the Gauss's law problem in E&M with the uniformly charged sphere, where you learn that it has a linear central force? Then they say if you did that with gravity, you jumped off right here, you'd go through to the other side and so forth, oscillate back and forth. Well, that linear attractive central force means that you have that potential. Now, if you have a dust cloud in universe, in the universe, then you're just applying, here's your star, and you're just applying Gauss's law to that radius, and that's why you're getting the same mathematics there. Okay. We'll probably do a little more of that later on, as a matter of fact. We can return to this one. That's a good one, because we will talk about Gauss's law either this semester or next semester. Okay, good. So that just gives some context. Now I did have another agenda. for today. So that gives all you guys something to work on, right? Some stuff, the first two problems in particular. Okay, so I'm going to remind you, what were we working on? What's the last thing in your notes before the exam? Just to bring us back to reality. It's actually related to these absolute angles and stuff. What do you got there?
The last thing I wrote was central force, where it was kind of similar to what you just did on question 4.
For the extended
Yeah.
body, right? Central force through the extended body. That's what we're doing now. And I'll just kind of review that. I think that we got enough time to get through the calculation, so. Force and extended bodies. Force for an extent. Force. There we go. Good. So the thing was this, we were working with, I'll just put you recall, we started with this extended body, namely a rod, a gravitating rod of length L. And we said, okay, we're gonna add up all of the potentials, so we're gonna use V equals minus G integral dm prime over r prime. This is our shorthand, okay? This is our shorthand, this is the one to remember, and then you build what you're going to do. So in this case, we had V of x was equal to minus G integral, the dm prime was m over L dx prime. And then the distance, 1 over that distance from, say, this point to that point, which I'm gonna just call x again, was x minus x prime. And so that's the one we worked on, and we were able to do it and analyze it. And what we found was we get minus G m over x plus something over x cubed. You get the x squared part in here, the x cubed. And of course, the derivative of this will give us the force. Right? M times the derivatives will give us the force. So then the next version of this, where we're gonna do this series, so we did some work on this. So this time, we've got some extended body, and we're going to take the origin at the center of mass. And we've got an R out here. We've got some point here, which we're going to call R prime. Point mass there at R prime. And we're interested in this right here. So this is R minus R prime, the vector. So the thing is, the potential at this point, due to that little red dot, is, all right, it's dV equals, and I can even say FR is equal to minus G dm prime, which is that mass at that point divided by R minus R prime. And I want to sum all those up, so I'm going to do an integral over the R primes from out here. That's my goal here. So V of R is equal to minus minus G integral dm prime r minus r prime over the entire body. And the important understanding is that we're taking the origin at the center of mass. Let's see what else. Yeah, what is this dm prime? That's some density d volume prime, not to be confused with that v potential, so whatever. We can say d3 if we want. d3 x prime. We're going to use Cartesian coordinates. So yeah, this is one point in space, and this is all of those are r primes, by the way. All of those points right here, and you're just adding it up. So as was pointed out last week, this could also be a sum, and you'd have, a sum for all of the point masses. You just have a sum and get that. In fact, we're going to do the summation formalism as well with the forces later on. But this one we're just jumping into like that, and it's been well motivated with these results right here. So the next task is to expand this thing into a Taylor series. And so there we're gonna get our money's worth. Okay? It's an interesting expansion. And once we've expanded it, we gotta monkey around with it a bit, and then we'll evaluate it up to second order. So what we're going to expand is this 1 over r minus r prime. So that's our next task. This is a calculation that's more commonly done in electricity and magnetism, but it's very useful in gravity as well. Okay, so what we're going to do is expand f of r plus r prime equals 1 over r minus r prime in a Taylor series. And the form we're going to use is this. F of r plus r prime equals. So we're calling r prime small, right? R is large. It's just like on my picture. We're far enough away from this object so that this r is much greater than any r prime in the object. So actually, let's go ahead and write that here. It's implied in the picture. Okay, it'll come out, right? So, but what this is f of r, which is to say when r prime is 0, plus the sum over df dxi when r prime is 0 at r times xi prime, right? Because I'm expanding in terms of this small quantity. And we have one more, and this is just I equals 1 to 3. We have one more 1/2 double sum I and j b squared f dxi dxj. Of course, those mixed partials will be symmetric. Pull this off. At r xi prime xj prime. And because I've got this as 1 minus, r prime, I'll just put negative xi primes in there explicitly. They'll cancel here and it'll give us a minus sign. Okay, so here's what we get. Well, first, we have to do d over dxi of 1 over r. Okay. This is something we've been working on also with our math methods. And I'll just write out what that is. So that's minus 1 over r squared. Then we need the chain rule d dxi of r, which is xi divided by r. So we have minus xi over r cubed. So that's that first derivative. Yeah, remember r was Now the mixed partial is interesting, so now we have d over dxj, d over dxi, 1 over r, right? So d squared dxj, dxi, or dxi, dxj, same thing. So now what do we have? We have to differentiate with respect to xj, so we get here a minus 1 over r cubed and a Kronecker delta ij. Because if I is equal to j, we just get a 1. If I is not equal to j, we get a 0. You know the Kronecker delta? Okay. You guys know the Kronecker delta, right? You remember? Let's fill them in. People learn. That's okay. This is an important sign. So let's go ahead and bring that into play. There's room right here. So this Kronecker delta, and here, let's write this out. So you know this Kronecker, this was a mathematician. Kronecker delta. So this delta ij is equal to 1 when I is equal to j, 0 when I is not equal to j. If you represent it as a matrix, it's just a matrix with the ones on the diagonal. Right? So yeah, that's what happened right here. I had 1 over r cubed, took the derivative with respect to xi partial, with respect to xj, sorry, of xi, so it's either 1 or 0. So 1 over r, minus 1 over r cubed, I have from here, delta ij. Then I have minus xi over r, no, I'm using the product rule again. So then I have minus xi, that's r to the minus 3, so I have minus 3 r to the minus 4. And then I'm doing the chain rule again with respect to r, so this time it's xj over r. So when the dust settles, we have here 3xi xj over r to the 5th minus, now I've got an r cubed, I'm going to go ahead and make that into an r to the 5th as well by writing minus r squared delta ij over r to the 5th. So we'll have a common r to the 5th right there in that sense. So this is going to be used in this part of the Taylor expansion, and this is going to be plugged into this one right up above there. So this goes into here. No, like that. This goes into here, and this goes in up there. That's the plan. If I write big, maybe I can put this all in one. Thank you. So now we'll do this. So now we have 1 over r minus r prime equals, first term is just 1 over r, right? R prime is 0. Second one is plus sum over negative xi over r. Those are our derivatives, xi prime, r cubed, sorry. And then the last one, 1/2 double sum ij. We got to plug this whole thing in. Got room here, 3xi xj, 5th minus r squared. Close call. Xi prime, got it, xj prime. So we have to do these things. Now we're going to take these 3 things here one at a time, okay? The first one, remember we have v of r equals minus g integral, I can just do the dm prime still. first one going to be? We just have that, so it's going to be minus G over R. I'm just plugging this one in. Integral d m prime. And I'll write underneath here what this is. Equals minus G m over R. Bingo, right? That is the first point mass form of this expansion. And right now it didn't matter that we were at the center of mass, but it will in a moment. So what comes after that is minus G integral dm prime, and we go in with this sum here, sum over minus xi over r cubed xi prime, I equals 1 to 3. I may save the last one for, right, plus third one. But now we're just gonna deal with this one. This one's interesting as well. What we can do with this, we can pull out, see, we're integrating over the prime, so we can pull out the r cubed. So we have minus G over r cubed. Then we have an integral dm prime sum over, and the, by the way, the minus signs cancel, I can go ahead and do that. We're gonna go ahead and go outside here, because what else are we not integrating over? The xi, so it's sum over xi integral dm prime xi prime. Okay, we have just enough time to discuss this one. First of all, is everything there in order? Minus signs cancel. Right, we're only integrating over the body. Okay. And these xi's are way out there somewhere. So does anybody recognize this? This would be the numerator of a center of mass calculation. Remember, the center of mass is like sum of mi xi prime over sum over mi for one of those, oops, one of those coordinates. Everybody recognize that as the center of mass? Center of mass. Important to recognize. I'll write this here. So maybe you've seen R center of mass. If you have a bunch of point masses, recognize the formula for center of mass? Yeah. Put it in your notes and make sure you look it up. Because what this is, it would be the numerator of such a, right, component-wise of such a expression with the integral. And if we chose our center of mass at the origin, this is 0. So that's a very important punchline. And if we were doing E and M, then this would be a charge density, and this would be called the dipole moment. But gravity has no dipole moment. Okay? Gravity only has one sign of mass, one sign of charge. So that's very important. So this is equal to 0, equals 0. Gravity has no dipole. No dipole moment. So the whole punchline of this is going to come next time, because we're going to do this term as well. This one's going to need a little work, but we've already gotten somewhere, because if you choose the origin at the center of mass, then you have the point mass property as your 0th order approximation. Okay? So we've already gotten a lot, but you guys will have this in your notes, and we'll throw this up on the board after the break, right? And the next term's gonna need a little massaging to get where we want it. But this is already a good point. Good point to stop. So, you guys have heard of gravitational radiation? Gravitational waves?
I mean, I've heard the term, I have no clue what it means.
Recent detections of that, okay? Well, it's a bit beyond this class, but the point is, when they detected them finally, they couldn't look for dipole waves, right? Because gravity has no dipole moment.
What I think predicted by Einstein.
Yeah,
Gravitational waves.
yeah, originally, it took a long time to get it. Anyway, we'll cut it short right here, perfect place, so we'll put this up on the board next time.
It's one of those things about for in general relativity, right?
Yes.